Hello, welcome to another module of this course, Analog Circuits. In this module, we are going to start a new topic, a new type of nonlinear circuits. These are known as multivibrators. Now, multivibrators are a special class of circuits for analog circuits, as well as they have their counterparts in digital circuits as well. In digital circuits, they are also known as flip-flops. But in the analog world, multivibrators are not just flip-flops, they have some other applications as well. So basically, the multivibrator circuit is a circuit that has two states. So one state, state number 1, state number 2, and depending on how these states transition from one to the another, we can classify the multivibrators into 3 different types. So let us see what are multivibrators. So suppose you have two states. These are just symbolic representations, these are not actual voltages or currents. So I just represent this line by state 1 as state 1, and this is state 2. So now this state 1 has to transition to state 2, and this state 2 has to transition to state 1. Now in a circuit, these states would correspond to some output voltage, which would be either high or low. If the output voltage is high, then I will say it is state 1, and if the output voltage is low, I will say that the circuit is in state 2, or vice versa. The important thing is, suppose each of these states are stable in their own right. That means, if the circuit is in state 1, then it continues to be in state 1 until I actually change something physically, manually in the circuit. So then it will transition, or I force the transition from state 1 to state 2. So such a circuit where both states are stable and I have to actually apply some stimulus to change from one state to another, and the change from one state to another is same for both states. That is, for changing from state 1 to state 2 also I have to apply a stimulus, and from state 2 to state 1 also I have to apply a stimulus. Such a type of circuit is known as a bistable multivibrator. If on the other hand, I need some manual input to change the state from state 1 to state 2, but once in state 2, automatically after some time the circuit will transition back to state 1. That is, only if say state 1 is stable, the other is not stable. If I go to the other state, then the circuit will after some time go back to state 1. Such a circuit is known as a monostable multivibrator. It is called monostable because only one of the two states that the circuit is in is stable, the other is not stable, the other will go back to the stable state. And then the third case is the case when no state is stable. That is, if I am in one state, then after some time I will transition to the other state, and once I am in the other state, again after some time I will transition to the first state. So such a circuit is known as an astable multivibrator. Now you might think that this astable is somewhat similar to this oscillator, isn't it, because after all we are going back to the first state. Yes, it is a kind of oscillator, but the difference between an oscillator and an astable multivibrator is that in an oscillator there is no concept of states of the system. That is, we can't identify any clear state in which the oscillator is. All at every time the output is changing, but at no point of time in the oscillator output can be clearly defined two distinct states. But in the case of an astable multivibrator, we can distinguish two clear states. So let us start from the bistable multivibrator, and slowly we will move on to the astable multivibrator. So, first thing is, in a bistable multivibrator we need to have two states. So, let us consider this circuit. This is an op amp, and this circuit might look very similar to the non-inverting op amp topology, but it is not. It is not because look at the point where we are applying feedback, it is to the positive terminal. In a non-inverting op amp, the feedback is applied to the inverting terminal, whereas in this case we are applying the feedback to the non-inverting terminal. So, this is a case of positive feedback. So, in positive feedback, recall from the discussions we had while discussing feedback, we purposely want to make the system unstable. We do not want to make the system stable. Now, going back to the circuit of an op amp, this is the circuit of an op amp. This is the equation for the output voltage, and as we know, the gain A, this capital A, the gain of this op amp is quite high. Ideally it is supposed to be infinite, but for real op amps also it is quite high. In fact, it is could be as high as 10 raised to 5. Now, on top of this we are applying positive feedback. So, what that means is we want the output voltage to get saturated. So, though the gain of this op amp is quite high, the output voltage will never exceed the saturation voltage. Okay. So, let us call the upper saturation voltage as L plus and the lower saturation voltage as L minus. Okay. So, L plus is the upper saturation voltage and L minus is the lower saturation okay. So, what it means is that if we draw the output voltage, then L plus is the maximum. Say this x is some independent variable which we shall see later on is the input voltage Vi, but if the y axis represents the output voltage, then L plus is the maximum positive voltage that can happen, that can be present at VO, and L minus is the maximum negative voltage. Now, usually as I had said earlier, this out L plus and L minus correspond to the upper and lower supply voltages. That is, suppose my supply voltages are plus VDD and minus VDD, then L plus will correspond to plus VDD and L minus will correspond to minus VDD. This is the rule, but not always true. If there is, for example, some drop from the supply voltage to the upper maximum permissible voltage, then L plus may not be equal to VDD, but usually it is. L plus is equal to the plus positive supply voltage and L minus is equal to the negative supply voltage. If my supply voltages were plus VDD and 0 volt, that is ground, then L minus would correspond to 0 voltage and L plus would correspond to plus VDD. So, now our circuit, from the circuit where we are applying positive feedback, our output voltage will vary from L plus to L minus. Now, how do we make this variation? So, let us go back to our circuit once again. As I said, for a bistable multivibrator, you need some external stimuli to change the output voltage. So, this L plus corresponds to one state, L minus voltage at the output corresponds to another state. If I change my Vi, then as we shall see, I can change, suppose my output voltage is L plus. By changing this Vi suitably, we can bring about a change in Vo. How? So, look at it this way. Vo is saturated, is at the, say Vo is at the upper saturation voltage L plus. So, then this voltage Vx, okay, this voltage Vx will be given by the voltage division of this this feedback circuit. So, Vx I can write it as okay. So, till the time my Vi, let us go back to this circuit, this is my circuit and this is the value of Vx. Till the time Vi is less than Vx, Vo will continue to be saturated and equal to the upper saturation voltage L plus. Now, suppose I keep on increasing Vi. If I keep on increasing Vi, there will be a point where Vi will exceed Vx voltage. Okay. When that happens, V1 minus V2 from this equation, this is V1, this is V2, becomes negative, and so the output will become saturated, but to the lower saturation voltage L minus. Okay. If we draw the graph for this one, so we have our output voltage, this is my Vi, this is Vo, this is L plus, this is L minus. Say initially the voltage, output voltage is at L plus. Okay. Now, I keep on increasing Vi, okay, such that at certain point there is a transition, and say the voltage value of Vi where this transition occurs, I call that Vth. Okay. So, at Vth, if I now use my green pen, so the curve will look like this. Okay. On the return path, however, So, let us go back to the circuit once again. So, Vx when Vi exceeded Vth, so Vth I can I have already written that. Let me go back to that equation where I have written it. So, when Vx is equal to V0 R1 upon R1 plus R2, this is the value of Vx. So, Vth will be given by L plus R1 upon R1 plus R2. Similarly, on the return path, when there will be another voltage which I call VTL, when Vi becomes lesser than this value VTL, a similar transition will occur. So, let us go back to the curve once again. See, when Vi is increasing, my Vo goes from L plus to L minus when Vi exceeds Vth. On the return path, when Vi goes below this VTL, so on the return path your V0 is at L minus, VTL is the voltage or the threshold voltage. If Vi goes below VTL, then there will again be a transition, because let us see here, let us go to the circuit. So, Vx is at the lower threshold voltage VTL, usually that is a negative voltage. Now, till the time Vi is more positive than VTL, V1 minus V2 will continue to be negative, and V0 will continue to be at its lower threshold at L minus. V0 will continue to be at L minus, and Vx will also continue to be at VTL. But when V0 becomes more negative than VTL, then V1 minus V2 becomes positive, and once V1 minus V2 becomes positive, V0 will go to the upper saturation voltage L plus, and so there will be a transition from L minus to L plus for V0. So, graphically that means when Vi is more negative than VTL, there will be another threshold, another transition, and the transition will look like this. Okay. So, when Vi increases, the path followed for transition will be this. When Vi decreases, the path followed will be like this. Okay. So, this is how this bistable multivibrator works. Now, we can make the, in this case, in this circuit that we have been studying so far, we have applied the Vi to the inverting terminal and the feedback is given to the non-inverting terminal. We can do the reverse also, that is, we can apply the input to the non-inverting terminal as well. So, then the circuit will be somewhat similar to the inverting op amp circuit that we have seen earlier. So, the circuit is, when the input is applied to the non-inverting terminal. In the previous case we had given the input to the inverting terminal, in this case we are giving it to the non-inverting terminal. Now, in this case it will be slightly different. The Vx value here is a combination of Vi and V0. Okay. So, Vx here will be given by Vi times R2 upon R1 plus R2 plus the contribution of Vo is obtained by shorting Vi. Okay. So, in this case the contribution of Vi is obtained by shorting Vo and then seeing what is the value of Vx. To find out the contribution of Vo to Vx, we short Vi and then find out the contribution of Vo. So, this will be Vo R1 upon, so this we know from the principle of superposition. Now, initially say V0 is at the upper saturation voltage L plus. Okay. So, when and say L plus is positive, so then Vx will also be positive. Okay. Now, if we keep on decreasing Vi, then from this equation we see that Vx will go on decreasing, and at one point Vx will go below the, so if I call this V1 and this as V2, at one point Vx will go below V2, that is the ground voltage, and the transition Vo will transition from L plus to L minus. Okay. So, what is that value of Vi for which Vx becomes lesser than the inverting input? So, that value is obtained by equating Vx is equal to 0, and the value we get is for Vi that we get is Vi is equal to minus V0 R1 upon R2, and since Vo is equal to L plus, so this becomes minus L plus R1 upon R2. Okay. This is not L plus R1, this is let me write it in a different way, so that it is L with a small subscript plus R1 upon R2. Okay. So, when this Vi becomes lesser than this value, there will be a transition. Similarly, when say V0 is equal to the lower saturation voltage L minus, and then Vx will is say negative. So, because Vx is negative, so Vo will continue, and Vx is negative and V2 is ground. So, V1 minus V2 is negative, and therefore, V0 will continue to be in the lower saturation voltage L minus. So, for that, to obtain the transition of V0 from L minus to L plus, we have to keep on increasing Vi, okay, till the value of Vi becomes equal to minus of L minus R1 upon R2. So, for Vi greater than this value, when Vi becomes greater than this value, V1 will become more positive as compared to V2, V2 is at ground, and therefore, V0 will transition from L minus to L plus. Okay. So, then graphically how does it look? So, we will follow the same procedure that we followed for the previous case, that is when the input was given to the inverting port. In this case, the curve looks similar. So, the difference between the previous graph and this one is the way the transition is happening. This is Vi given to inverting input. So, in this case, when Vi goes high, the transition of V0 is from L plus to L minus and vice versa. In this case, when Vi goes high, the transition of Vo is from L minus to L plus and vice versa. Now, one thing I want to what is interesting here is is that why do we have such a system? After all, if we wanted a transition between L plus and L minus, we could just obtain it with a like this, isn't it? This circuit will also cross a transition from L plus to L minus. When Vi is greater than 0, V0 will be L plus. When Vi is lesser than 0, V0 will be L minus. Why not choose such a simple circuit over these more complicated circuits that we are discussing? To understand this, let us see how a normal analog signal is. Now, ideally, we want a signal which is like this, a very clean signal. If this is the input signal, okay, this sinusoidal looking signal, then we really don't have a problem with this circuit that I just gave. Here, whenever my input is greater than 0, V0 will go to the upper saturation voltage, and when Vi is lesser than 0, V0 will go to the lower saturation voltage. But in reality, this kind of signals that you get are like this. Suppose you have your input signal like this. Now, in this case, you see any time, even though the general trend of this signal is downwards, because of noise, the signal first of all is distorted, and there are occasions, there are time instants when the signal actually becomes positive, even though its average value remains negative. Now, in this kind of circuit, if even for a moment the input becomes higher than 0, then V0 will undergo a transition, which is what we do not want when we have a signal like this. In this case, whenever the average value of the signal or the mean value of this signal is negative, we want the output to go to the lower saturation voltage. So that is why in the proposed circuits that we had discussed, both for when the input is given to the inverting as well as when the input is given to the non-inverting inputs of the op-amp, a certain gap is there between Vth and Vtl. So for this signal, this would translate to something like this. What we enable by this circuits is that even if for some noise present, if suppose the input voltage momentarily crosses the 0 mark, both positive and negative, but still remains within this gap Vth to Vtl, there will not be an abrupt transition, which is anyway undesirable. So just to prevent these spurious transitions, which we do not want, these undesired transitions, that is when for some noise, suppose the signal goes momentarily high above 0 voltage, even though the average value or the mean value of the signal is negative. So to avoid this, we need such a circuit. This kind of characteristics is also known as a hysteresis. Instead of calling this gap, we also call it as hysteresis. That is, when we are increasing the input voltage, the path followed by the output voltage is different from the path followed by the output voltage when we are decreasing it. Now, this kind of circuit that we discussed just now also is referred to as a Schmitt trigger. This bistable multivibrator is also known by the term Schmitt trigger. So in this module, we covered the topic of bistable multivibrator or the Schmitt trigger, and we saw that we need to actually give a manual or physical stimuli to cause the change from one state to another. In the next module, we shall cover the other types of multivibrators. Thank you.